Okay, good morning everyone, and welcome to Office Hours for World Quant University. This is for Unit 1. To be clear, it's a question that came up a few times last time, so just to recall, this is Unit 1. I just want to make that as clear as possible. No particular agenda for today. I'm going to take a look at the World Quant Ask website and see if perhaps there are some questions that we can start addressing in there. But otherwise, as per usual, feel free to add any questions you do have in the chat, and I'll be sure to get to as many of those as possible. Alright, it looks like there are a few things we can address in here. Should I answer these kind of in chronological order? Perhaps see if some of these maybe don't have many answers. Someone asked, is this Unit 2? No, so this is Unit 1. Mondays and Wednesdays at 8:30 is Unit 1 office hours. Someone is asking about conventions using Python 3 versus 2 and why it's still recommended to use super of class and self instead of the simpler super function when doing object-oriented programming. This is ultimately, a little bit of a stylistic choice, tending towards just more explicit expressions, in code tends to be a little bit easier to, while it perhaps is harder to, might be harder to, maybe remember the syntax in writing, but tends to be a little bit easier to read because there's just more information sort of visibly on the page. Let's see, some questions coming in the chat. What is the best Linux distribution for data scientists? I would say likely it does not make a huge difference. Ubuntu is very user-friendly, and it's also widely used in server settings. I think Fedora is also used sometimes in some more server settings. I think it might be a little bit more lightweight than Ubuntu. If you are looking for something with like a nice graphical interface that still sort of, works well, like I guess more server style Linux stuff, though Ubuntu is really nice. I use Linux Mint, which is really just a sort of different skin on Ubuntu. It's designed to look a little bit more like Windows, although I also typically use OS X, so I don't know that that's a big appeal directly for me. I find Linux Mint a little bit easier to navigate than Ubuntu, but those are both great. Arch Linux is certainly used a lot in more like server applications. So. I can take a look at some more of these questions here. I think some of these do have some answers, but we can just maybe go over. So this is probably coming from the introductory materials. We note that on some questions you may be able to score greater than a 1 with our grader service. So I guess, why is this sometimes possible, or are there clues to when this is possible, or is there a reason to try to go greater than 1? what I would generally recommend here, firstly, to my knowledge, anytime that you can score greater than 1, that's actually going to be in a more machine learning context where we're scoring your supplied model against a reference model that we have built. As someone noted in the answer down here, we probably don't need to worry too much about scoring more than 1, or about scoring, let's say, 1 versus, 0.99 or 95 and so forth. The grader is in many ways looking for big ideas. And a lot of times there are small differences between a 0.95 and a 1, or maybe a 1 and a 1.1. And getting over that 0.9 or getting closer to a 1 threshold is demonstrating that you have a strong grasp of those big ideas. And once you're at that point, if you do want to spend more time going the extra mile, really I would recommend doing things like revising your solutions not for more points, but for more readability or expressiveness. Or just spending more time, going back through the lecture notebook or investigating more deeply into the documentation for the libraries we're working with. That's kind of what I would say on that. All right. Someone has a question. Okay. So Ankit is asking, and Ankit, I will try to address this. I don't know if I'm exactly clear on the context, but Ankit is saying, and perhaps, Ankit, this might be related to renaming, or it might be related to using the word list as a variable. But Ankit was saying, and I'm going to start by calling it something else. Ankit was saying that they had a list that looked something like this: 1, 1, 2, 3, 5, 8, 13, and was calling something like this. And I don't know if I'm exactly sure. Okay. So Ankit, you're saying that you were surprised to see this result after creating it, and I'm calling it my list. I can make a note as to why I'm not calling it list in a second. So you're saying that you had created a list 1, 1, 2, 3, 5, 8, and 13, and you were saying, all right, so let's print this out, and I want to index into my list, and the index I would like to use, well, I'd actually like to get it by indexing into my list again at index 4. So let's take a look, maybe unpacking this code here. So first off, the index that we're putting into this bigger one, right? My list index 4. Well, we index from 0 in Python, right? So we have 0, 1, 2, 3, 4. And so my list at index 4 is going to be, well, it's always good to run our code blocks now, isn't it? It's going to be 5. And Ankit was unsure as to why 8 was coming up in here. But that's precisely because when we say my list 4 inside these brackets, we're substituting for here a value of 5. And that means that if we were to put 5 here, well, that's going to be 8, right? Because we have 1, 1, 2, or I'm sorry, 0, 1, 2, 3, 4, 5 in terms of the indices of this list. So Ankit, hopefully that answers your question. I think likely this has to do just with just with that zero indexing, especially if you're coming from a different programming language, perhaps like R or MATLAB. It can be just sort of a reflex that one has to get used to. I started mostly programming in R, which is 1 indexed, Python is 0 indexed, so it take me a little while, just, through repetition, just kind of becomes a reflex, or a habit, I suppose. I also want to touch on really quickly before I look at some other questions that I had renamed the variable that Ankit had given in this question from just list to mylist. And this is something that applies in a few different places in Python. We see here that list is highlighted in green when we write it in the Jupyter Notebook. This is because it is a keyword in Python. It's like a reserved word from Python's built-in module or library. List does something special, right? List is sort of reserved for as a list constructor. We can use it to cast things from perhaps a tuple into a list. And Python is not going to stop us from overwriting the value of this variable. So if I were to say something like list equals let's say, well, I guess let's use this example. So if I overwrite this value, Python's not going to stop us. And now I would not be able to use this original and intended meaning of list. So now if I try to run this code again, we would say list object is not callable. And that's because list used to be a function, and I actually made list into a list, so I can't use it as a function to turn this now into a list. This is going to be the case with things like, well, anytime you see something in green, essentially. Things like print, things in fact like ID. And so we need to exercise some caution there. And so that's the reason that I changed list to mylist in this example. Turnam asked, there are 10 videos in the course platform from Intro to Data Structures. These are to be completed in the first week. Yes, so each week the new videos will be sent out so that you can then get into the new lectures. And Ankit also asked about something like, in RStudio, we can remove things from the global namespace, actually, which in R is more referred to as, we say more like an environment. And sure, so using rm in R would basically delete a variable. And we do have something similar in Python, the del for delete keyword. So for instance, if I had some variable x, let's print out x. And now if I said del space x, that deletes x. And now if I tried to print out x again, it's going to say that x is not defined because it's been deleted. So that would be the analog to rm in Python. I would encourage you, and I would actually say the same thing in R, that I would encourage you towards working in a less perhaps interactive and more like function-based or script-based way. And in many cases, we don't really need to use things like DEL. And in fact, in R, we can often get away without using RM if we just if we only want a variable temporarily, perhaps it should live inside a function rather than in the global namespace or base environment, to use more like R terminology, which is a little bit off topic. Raj asked, so my programming journey includes R and Python. How would I rank R or Python, or I guess as you've asked it, is R superior compared to Python in data visualization? Here's what I would say. R has a wealth of like great data visualization tools. Things like, ggplot2 is a fantastic plotting library, certainly. And actually, ideas from ggplot2 have gone on to be very influential in a lot of other packages. R Shiny is great for creating kind of straightforward interactive web apps and dashboards. And that's a little bit more integrated into like R kind of basic R workflows than maybe something similar in Python, partially because RStudio integrates it pretty well. That being said, Python has a more broad range of data visualization libraries that it sort of plays nice with. Things like Bokeh, Bokeh, things like Altair, Altair, are both popular and very flexible. Bokeh is a very, very powerful visualization library that we can use to create like rich dashboards and actually really sophisticated data viz applications. It gets complicated very quickly. It relies on a lot of web development to make things really powerful in Bokeh. So if your goal is to get a dashboard off the ground very quickly, R Shiny is great. But if your goal is to integrate into other web applications, working with something like Bokeh might be a little bit more flexible and actually powerful. Andre asked if you finished the mini projects in Python, should the mini projects from data wrangling be completed this week? So to that, we can refer to the syllabus. It will actually be a while from now that we're really worried with the data wrangling mini project. So there's a few weeks kind of oriented in the Python directory. If you have worked through all those mini projects, it's fantastic. I would recommend spending some time, again, revisiting the way that you wrote those solutions, looking into things like, the code style, and, from there, maybe diving back into lecture or diving more deeply into other things you can do with the sorts of, libraries and such that we've been covering. So no, you do not need to, and I wouldn't really advise maybe working that far ahead. You're more than welcome to if you'd like, into data wrangling. I would say if you are done with the Python mini projects, it's a great thing to do to just spend more time kind of working in adjacent topics to the stuff we've already done in lecture. Ryan asked what we should complete by the end of this week, and that's going to direct us back to the syllabus as well. We say that we've assigned this mini project, or these two mini projects in week 1. That does not mean that you have to complete it this week. Technically, they're all due by the end of the course on December 4th. However, I would say maybe during the next week, it would be great to try to get these done. When we assign them, it means that it is during or after this week that we've covered all of the material necessary for the mini project. So by the end of this week, you certainly should have watched all the lectures, and if you're done with that, I would say it would be great to start looking at these mini projects, but don't think you need to have them finished this week. Jeremias asked, where are the mini projects? So in your data course directory, if you are at your Jupyter Hub pod, in data course, we have these two directories in here, Python for our foundational Python curriculum, data wrangling for things getting more into pandas and SQL. But in Python, we have a mini projects directory. And we'd have the IN, IP, and VC mini projects, for instance. And the three of those are this week's and next week's mini projects. And then PW is found, that's where we start working into data wrangling. That's going to be week 3. But essentially, in your Jupyter Hub server, data course, Python, mini projects, or data course, data wrangling mini projects. And they're going to be right there. Sindura had also asked a while ago, are there additional things taught in office hours? I would say yes and no. We would largely be reinforcing concepts and just answering questions that have been brought up in office hours. In some cases, maybe there might be one or two things that are not explicitly covered in lecture, but I would not be going into, and my colleagues would not be going into, other broad topics in office hours. And let's see here. Yeah, we actually would like to look at IP for this one. So there was a question earlier about exercise 4 in the, I believe that one is referring to the IP mini project. Working on this is prime, and I hope I am. Okay. And so the question is, I think perhaps for an explanation about optimizing, pardon me, about what we should be doing in this problem. So in is prime, we're, checking to see if a number is prime. And for rather large numbers, this is slow. The reason for this is that we check every single possible factor for the tested number. And we're going to try to make that a little bit faster when we write this is prime fast function. So this is going to involve, changing the conditions or maybe the sequence of conditions we can check. For instance, we know that if a number is even and it's greater than 2, or I guess if it's just not 2, we already know it's not prime. So perhaps one thing we could do before anything else is just in our new function, we should check if the number is even. Maybe check if it's 2. If it is 2, return prime. Then otherwise check if the number is even. And if it is, well, we know it's not 2 and it's even. So we should return, false. And then as a result, if we, if the number is odd, well, then we should only be looking at odd factors. And so, if we consider why this happens, let's say, well, n is any number, right? And it has, let's say, two factors, a and b. And so we can consider n as a prime number. We can consider n as a composite number, which is to say a number that is not prime. And so, if n is not prime, then a and b could be something other than n and 1, right? A prime number has two factors, itself and 1. So there's nothing else that would work for a and b except for these two values. If n is not prime, then we'd have some two factors other than n and 1. And when that happens, well, we know that if a is greater than the square root of n, then b has to be smaller than the square root of n. This is the main idea we're going to be making use of. And the reason for this, well, let's consider a number like 9, or perhaps, let's see, let me think. Let's consider a number like 16. 16 has a few different factors, right? Obviously 1 and 16. We can also factor 16 into 2 times 8 or 4 times 4. So, square root of 16, of course, is 4. And we can see that if a is the square root of n, then b is the square root of n, right? 4 and 4, 16. But once a, this first factor of 16, is larger than 4, well, if we wanted to multiply a number that was larger than 4 by some number b, and we wanted it to be equal to 16, well, clearly b has to be less than 4, right? Because if a is 4.1 or 5 or anything, or 8, for instance, well, we definitely can't multiply it by 4 because that's going to be bigger than 16. We can't multiply it by anything bigger than 4. So b has to be less than 4. And this is the basic idea. As a result, we can just check these possible values for b, basically. We only need to check up to the square root of n. If we go past the square root of n and we find any factors that work for n, we would just be repeating something that we already saw. So we can check b is equal to 2, for instance. We would find that we can split 16 into 2 and 8, right? We wouldn't need to check anything like 8, because at that point, the other factor, we already would have seen it. We would have found its match, because we've passed the square root of n. So that's just going to say that we're going to be, in this entire paragraph, we're defining how we can limit the number of potential factors that we need to test. That's kind of the basic idea. Someone asked if I'll be teaching next week office hours or Dawn. Dawn is going to be on office hours as of next week. Someone also asked that the previous office hour has not been uploaded. I will take a look into that. It should have been, but maybe something had gone wrong, so I'll try that out. I'll have to look into that after office hours, but it certainly should be up there. I'll just double check that everything ran correctly, and if there were any issues, I should be able to get it up right away. Someone also asked, they're having some issues with the kernel restarting, working on the DW mini project. And I can say that, we test all of these notebooks to make sure they run correctly and the kernel should not die with any of the necessary operations, and there's definitely a lot of leeway there. So one thing you might want to check is you might want to check this running tab, which would let you know if you have anything well running, any other notebooks where the kernel is still alive. If you do have other notebooks running, and you've been doing, a number of computations or storing pandas data frames, which might take up a decent amount of memory, then your mini project notebook, DW, might be competing for resources on your server. And that's a very common issue as to why the kernel might die. If your server died and you can't restart it, and if that's referring to from this Start My Server page, sometimes we do have some slight delays. The way that we provision these servers on AWS can sometimes have a slight hiccup as we're scaling up the number of machines we use. You should be able to restart it if you're having issues with Start My Server. Should be able to restart it in just a few minutes. Someone also asked about going over some of the VC stuff for next week's mini project. I'm going to delay on this for now. Certainly in a future office hour, we can talk about some of this stuff, but because VC is an upcoming mini project, it's likely that many people haven't gotten there yet, and also likely that as we go through more lecture, some of those questions may be answered just by the material we go over. Okay, so I'm just watching the chat here. If there are other questions, feel free to paste those in the chat. Can I talk about recursion? I likely could talk about recursion. That's a very broad question. So I don't know if I have, can I explain recursion? Okay, still maybe a little bit of a broad question. I can try to address recursion from a general standpoint, hopefully with a sort of illuminating example. But I don't have a recursion example that I would immediately reach for off the top of my head, so might need to take a minute here. Basically, though, recursion is a so this is sort of like a programming paradigm in which a function calls itself. So a function would probably look something like this. We would have some arguments in a recursive function. So I'm just defining a function. I've called it recursive function. Of course, this has nothing to do with the fact that it's recursive. It's just a name that I'm using. A recursive function will have two things. It will have a stopping condition, and it will have a recursive step. Stopping condition returns a value without calling the function again. Recursive step calls the function again from within the function. So what does that mean? Well, Oh, and I guess we might also have, you know, well, no, that's kind of what it looks like. I'm going to write a really silly recursive function here. Returns true if x is greater than or equal to 10. Otherwise calls x plus 1. That's one thing we could do. Ryan has a more involved example with the Fibonacci sequence, which we can address after this, but I think that a sort of trivial recursive function is a good place to start. So we have a stopping condition, and I'm saying that this function returns true if x is greater than or equal to 10. So in other words, at this point, if x is greater than or equal to 10, we're basically going to exit the function without calling recursive function again. So I'm going to say return true. We might think of this as a stopping condition. We might think of this as a base case, but it's something that would happen that would cause us to exit and return some value. You need this in a recursive function. You need a way of not calling x again, not calling recursive function again. Otherwise, if we don't meet our stopping condition, we're going to return the value of the recursive function. And I'm saying if this doesn't happen, we're going to return the value of recursive function x plus 1. And if I run this, at 1, let's think about what happens. Well, let's say I run this at 9. Let's think about what happens. I've passed in 9 for x. The first thing that we run into is a check to see if x is greater than or equal to 10. If it was, we would return true, and that would be the end of the story. But it's not true. X is 9, it's less than 10. So this never happens. As a result, we're down here now. And we're now calling recursive function, and that's the function we're currently inside of. We're saying, okay, well in that case, return recursive function evaluated at x plus 1. Well, x is 9, so x plus 1 is 10. So what is this value? Well, we have to go back into another call to recursive function to figure that out. So now we're saying recursive function with x equals 10. 9 plus 1. Well, if x is greater than or equal to 10, we return true. And it is, because x is 10. So we return true. So in our recursive step, now we've recursed into the function, when we called recursive function 9 plus 1, that is now true, and we're returning that, and it's now true. So if I run this, this is true. If I ran this from 1, well then I would say this doesn't happen when x is 1, so I have to return recursive function 2. This doesn't happen when x is 2, so I have to call from within that step recursive function x equals 3, or 2 plus 1. Well, 3 doesn't trigger this if statement, so now we have to call recursive function 3 plus 1. And we'll keep working inwards, recursing, inwards to these nested calls until we reach our stopping condition, until x becomes 10. And when it does, we'll return true. And when that happens, it will filter back up through all of those nested calls to our recursive function. And it finally will return true. And we could see that if we did something like this. And here I have to think, how do I want to do this? Oops. I should populate that value in. So we called recursive function of 1, but that just means that we ended up calling recursive function at 2, and then 3, all the way up to 10. Here's one thing I could do. To make this look a little nicer. Oh, that's a little bit too much. So we called recursive function 1. We needed to return recursive function 2, which means we had to call recursive function 2. And from there, we had to return recursive function 3, and so forth. And we do that until we stop. So Ryan asked, does that mean recursion is a loop? Not exactly. Recursion can do something very similar to looping. And in this case, it does something exceedingly similar to looping. This is something we could really easily have written as a while loop. While x is less than or equal to 10, x equals x plus 1. If x equal, or, otherwise return true, right? It's actually always the case that there is some way of solving a problem. Any problem that can be solved with recursion can be solved with iteration, with a loop. It's also the case that any problem that can be solved with iteration, a loop, can be solved with recursion. That's a computer science proof. I'm not going to get into like theoretical computer science here, but that's the basic idea. So this is a kind of a boring recursive function. Let's look at a more interesting one. Let's look at a recursive function for the Fibonacci sequence. And let's see. How do I want to do this? I think I know what the first line I typically would want to use here is. I think our stopping condition is simply, well, let's see, what is our Fibonacci sequence, right? Our Fibonacci sequence, this is a special, additive sequence, or this actually is a recursively defined sequence. And it's defined like this. It looks like 0, 1, 1, 2, 3, 5. It's going to be 8, 13, 21. I guess that gives us 34. Hopefully I haven't made any mistakes here. But essentially, the Fibonacci sequence is given by, well, it has these two numbers to start with, 0 and 1. Those are our base conditions. In a recursive setting, those are our stopping conditions. After this, essentially, each Fibonacci number, the third number in the Fibonacci sequence, is given by the sum of the previous two numbers. So here 1 is 1 plus 0, and here 2 is 1 plus 1, and here 3 is 1 plus 2, and 13 is 5 plus 8, and so forth. So that means that the ith, or nth perhaps, I like saying nth better than ith. And let's call this, I don't know, just f of n. When n is greater than or equal to 2. The first one is 0, the second one is, I'm sorry, when this is just simply greater than 2. So if n is 3, then the third Fibonacci number is given by the n minus 1, so second Fibonacci number, plus the n minus 2 first Fibonacci number. This is a recursive step because we have f, and to get the value of f, we had to call f twice, in fact. Let's also say if, this is the, and again, this is the nth Fibonacci number, then the first Fibonacci number and the second Fibonacci number are equal to, or I'm sorry, the first Fibonacci number is 0, and the second Fibonacci number is 1. But when n is greater than 2, maybe I'll write this way. The Fibonacci number is defined recursively. We can write this as a function. There's certainly nothing stopping us, right? We need to encode these. We need to encode this. This is a stopping condition, and this is a recursive step. So I'm saying give me the nth Fibonacci number for n. I'm indexing from 1 here, if you would like to call it that. This is the first Fibonacci number, this is the second one. So I had these two stopping conditions. These are not defined recursively. These are defined literally. So if n equals 1, I have to return this value. The function, right? If n is 2, I should return 1. 0 and then 1. But once I'm done with that, every single Fibonacci number is the sum of the previous two numbers. 2 is the sum of these two numbers. 3 is the sum of these two numbers. 21 is the sum of these two numbers. So if I haven't gotten into this situation, I can just return this. That's just what we've defined here, right? And that would give us, if n was 3, it would give us the nth Fibonacci number, n minus 1, where this is now 2. Nth Fibonacci number, n minus 2, this is now 1. So let's try this out. This is 1, because neither of these things happened. So we returned this with n minus 1, 3 minus 1, which puts us here, plus this function with n minus 2, which is 1, and that puts us here. And of course, that is our third Fibonacci number. If I did the fifth, well, let's do this, I guess, let's build it up. If I did the fourth Fibonacci number, this is 2. So here's what happens. We have 4 here. Neither of these things are triggered. So we end up here. So we have to say, all right, the fourth Fibonacci number is the n minus 1 third Fibonacci number plus the n minus 2 second Fibonacci number. Well, the second Fibonacci number is 1. 4 minus 2 is 2. So over here, we just end up right here. And we return 1. This is now 1. But here we had 4 minus 1. And so we said nth Fibonacci number at 3, the third one. Well, for the third one, neither of these was triggered, so we had to do this. And now we had 3 minus 1 and 3 minus 2. So this, well, in order, this, 1, plus this, 0. 1 plus 1 is 2. So this was 1, which we saw before. This was 1, which is just explicitly encoded, because this, 4 minus 2 is 2. Or we could do the nth Fibonacci number, and let's say the 8th. But it's doing the same thing over and over again. The 8th Fibonacci number is the sum of the 7th and the 6th, but the 7th is the sum of the 6th and the 5th, and the 6th is the sum of the 5th and the 4th, and so forth. All the way until we get to here. I'm going to quickly touch on Ermias' question about the modulo operator, but I also want to, in concluding with the nth Fibonacci number, just on the coding style here, what's the difference between saying if in two separate if statements versus making this an elif statement? Functionally, in this case, there is no difference. We could have made this elif. I tend to use elif only when I have like an else statement, but I also tend not to use a whole lot of else statements. because, well, it sort of depends. If we're returning out of a function, then if this happens, we return and nothing else happens. So if this happens, we return, we don't even check this. If this happens, it means this didn't happen. And if this happens, we return and we don't do this. So you will often see people write their conditional expressions in this manner. It's just a little bit convenient because it basically saves us additional indentation. Like I could have written this like elif, and then I could have written this else, but then I would have had to indent this, and I would prefer, since it does the same thing anyway, and a lot of people just kind of stylistically do this, especially like if we have return statements, it does the same thing as separating these into distinct conditions. So to save additional indentation, which makes it harder to read stuff, you will see something like this. Okay, the last question that I have time for has to do with the following code. So this is Ermias' question in the chat. So we have the code for factor in range from 2 to number, and we have to define number. Let's say number is 6. If number modulo factor equals 0, and Ermias gave not a whole lot of, like, didn't say what to do if this happens, so I'm going to print something out. And I'm going to do this. Oops, that should say F, not R. I'm just going to print a new line. So factor and number here. These are just variables, right? So number is 6, so range is giving us 2, 3, 4, and 5. And factor is every one of those values as a variable in our loop, right? So first we will do this. I'm going to put these outside of this. So number is always 6. Factor is 2, 3, 4, and 5. So then we're checking number modulo factor. And when we have 6 and 2, well, we have 6 modulo 2, that is 0, because 6 divided by 2 is 3. There is no remainder. And so we print this out. Is the question, oh, how this relates to prime numbers? Okay, that's a separate question. I thought you were asking about just the code, because you didn't have any other context for where this is happening. So as a result, how does this relate to prime numbers? Well, if there are, yeah, I guess that's a fair question. Something like this, return not prime. So this is not the best way to do an isPrime function, but basically, here's what happens. We need to check, and we could check actually fewer numbers than this, but this is the most basic version. We need to check if there are any factors of number. And if number is 5, we need to check, is 5 divisible by 2? Is it divisible by 3? Is it divisible by 4? If it was divisible by any of those things, then it would have a factor that was not 1 or 5, and it would not be prime. If we had 6, we would have found out that 6 divided by 2 is 3. In other words, 6 modulo 2 is 0. So 6 has a factor other than 6 and 1, so it is not prime. It is composite. So that's basically what's happening. We're looking to see if there is a different factor for a number than itself or 1. And if there is, then we know right off the bat it can't be prime, because that is literally the definition of a prime number, is it only can be divided by 1 or itself, or only can be expressed as the product of 1 and itself. Alright, it's a little after 9:30 here, so I'm going to close out. Thanks everyone for the great questions, and I will be sure to check out what happened with the previous video, make sure it gets uploaded, make sure this one gets uploaded as well. Alright, so thanks everyone. You have a great day.